All right, so let's get started. Once again, please take out your phones and shut them off. We're going to talk about integrals in dynamics, the use of integrals in dynamics today. Before I do that, are there any questions on the stuff we've talked about last week? Integrals in statics, integrals in engineering in general. So I think if you're going to remember one thing about integrals, remember that it's simply the opposite of the derivative, and the integral of a function is simply the area under the curve described by that function. So today we're going to talk about dynamics. I'm going to go over a couple of examples that you've already seen, but in reverse. So I know Dr. Pilipacum talked about derivatives in dynamics, and he went through some examples. And this is the same example, but in reverse. So in this case, we've got some object moving in the direction of x at some velocity and some acceleration. The position is x of t, the velocity is v of t, also known as the derivative of position, and the acceleration, a of t, is the derivative of velocity. This is all information that Dr. Pilipacum had gone over. In that case, I believe he gave you position and time, and you found the velocity and the acceleration. Well, in this case, if you know what the acceleration is, how do you get the velocity and the position? You find the integral. So if you know what acceleration is, you take the integral of this in order to find velocity. So the integral of acceleration is the integral of dv dt. What is the integral of dv dt? The integral of a derivative. What is that? The integral of the derivative of v with respect to t.
Maybe x plus c?
Not x plus c. So this is a very generic question. It's not specific to any particular function.
It would just be the function of t with respect to v.
The function of v with respect to t, yeah. So the integral of the derivative is the function, right? If you have a function and you take the derivative of that function and then integrate that, you get the function, because integrals and derivatives are the opposite of each other. So we have a of t, and we want to find velocity and position. So we know from this that the integral, that a of t is equal to dv dt. If we integrate both of those from 0 to t, whatever time we want to choose as our endpoint, we can find the velocity. So by definition, dv dt is equal to that function. The integral of the derivative of velocity with respect to time is equal to that function, velocity, with respect to time. So this integral is simply equal to the function evaluated from 0 to t, which is equal to this integral. We plug t into the function for velocity, and we plug 0 into the function for velocity. And all we need to know is the initial velocity and that function, which we need to integrate, and we will get the velocity at any given time. Does that make sense? It's pretty straightforward. We're just going backwards from what Dr. Pilipacum had described. So the next step is to find the position. And again, it's the same process. The derivative of position with respect to time is equal to the velocity. So we can find x of t now that we know the velocity that we just found in the previous slide. Take the integral of both sides. The integral of this derivative of x with respect to t is x evaluated from 0 to t, and the integral of v of t dt. We don't know what v of t is yet, because all we know is a of t. It's some function. But whatever that function is, we can evaluate that integral, add the initial position, and find the position at any given time. So this is pretty straightforward. I think it is anyway. Are there questions on this information, on these slides, on how to do this? So if this is the general process, we can go back to that example that Dr. Pillip-Packham had used. In this case, we've got a ball that's dropped from some height, from a meter height, at time 0, and we're given the acceleration, minus 9.81 meters per second squared. It's the acceleration due to gravity. And the question is, what is v, what is y, and what is the time to impact? Find the expression for the velocity at any given time, the expression for position, and the time to impact. Well, we're going to integrate that to get velocity. Again, dv dt is equal to a of t, and a of t is minus 9.81 meters per second squared. What is the integral of minus 9.81 meters per second squared with respect to t? Sir, here, in the brown shirt. What is the integral of minus 9.81 meters per second squared with respect to t? So integration is, in this case, it's simply t to the, this is minus 9.81 times t to the 0, because t raised to the 0 power is 1. So integration is simply raising the exponent by 1 and then dividing by that. So minus 9.81 times t to the 0 is equal to, the integral of that is minus 9.81 times t to the power of 1 divided by 1. All right, so minus 9.81 t is that integral. The integral of dv dt is v of t. So we evaluate these from 0 to t, and we find out that the velocity at any given time minus the initial velocity is equal to minus 9.81 t minus 0, because minus 9.81 times 0 is 0. So the velocity at any given time is simply equal to minus 9.81 times time, because in this case we were told the initial velocity is 0. That was given in the problem statement. If it was not 0, if the initial velocity was not 0, you'd have to include that. This would be your final answer. So at 2 seconds, the velocity is going to be minus 9.81 times 2, which is going to be, I don't know, 19 point something. So this is the equation for velocity. In order to get position, we go through the same process, except now we're going to take the derivative of position with respect to time is equal to velocity, and we just figured out what velocity is, so we can integrate both sides of this. From 0 to t, velocity is a function of time, as a function of time, is minus 9.81. Do you guys have something to share? Or do you have a question? Yeah?
No, I had a question on the previous slide. But
This slide?
the one actually before that.
Another one? Go back?
When you put t of 0, is it always going to be, you always put it in 0 as in the starting point? Or?
Not necessarily. In this case, we were told that it's dropped from a certain point. So you can assume that if it's dropped, it's starting at an initial velocity of 0, right? Because you're holding it, and when you let it go, that instantaneous moment in time, the ball it has a zero velocity right as you drop it, and then it picks up speed. There may be instances where you're driving down the highway. This could be a problem where you're driving down the highway. You've got some acceleration. You're starting at 50 miles an hour and you try to pass somebody. Your initial velocity then is 50 miles an hour, and your acceleration might be 10 miles per hour per second, which would be pretty fast. But yeah. So this is only zero in this case because it's given as zero. All right. So this integral, minus 9.81 times t, what's the integral of minus 9.81 times t?
So it would be 9.81 divided by 2 times t squared?
Yes, exactly. And then we're going to evaluate that from 0 to t. So remember, the integration of this function of any variable raised to a power is simply to increase the power by a factor by 1 and then divide by it. So t to the 1, integrate that, t squared over 2. All right? The integral of the derivative is simply the function. So when we evaluate this integral, we get minus 9.81 over 2 times t squared. And we evaluate this from 0 to t. In this case, the initial position, let's see, we're going to solve for the position at any time. This function evaluated from 0 to t, again, minus 9.81 over 2 times t squared, and we're going to subtract minus 9.81 over 2 times 0 squared, so that's 0. That just drops out. Move this value, this initial value of position, to the right-hand side so that the position at any time is equal to the initial position minus 4.905 times t squared. If your initial position is 0, then that drops out. If it's not 0, you can't drop that out. You need to keep it. And in this case, I think the initial position was given as 1. Yes?
So where do we, like, in the problem, how would we find like, the initial position?
So you have to go back to the problem statement. So let me go back to here. Dropped from a height of 1 meter. Now, if that's what you're told, it's up to you to set up the coordinate system and the origin. The obvious thing, I think, the simple thing, is to make the y equals 0 at the ground level, so that then the initial position is y equals 1. You could make the 0 position y equals 1 meter. But then you have to keep that in mind when you try to calculate the position as that ball falls, because it's always going to be a negative value. And you're going to have to keep that in mind. So the simple thing is just at 0. Okay.
Like when you started with the acceleration, you're not going to have like, you're not going to be able to get a value that's other than that. So like, how do you get the original position equation? You know what I mean? Like the quadratic. Because you know how like you went backwards? Like where does the 1 substitute in? Like if you don't start at 0?
Well, if you don't start at 0,
Like, if we were getting like the minus y to the 0 value, minus 4 point whatever t squared, that was our answer. But like
this.
Like, yeah, what if we didn't start at 0? Like, would we just put in the y?
Well, if the initial position was 0, if you set your coordinate system so that the ball started at 0, then you just plug 0 in here. If you set the coordinate system so that y, the initial value of y is 1, you set this becomes equal to 1. Yeah, okay. All right. So in this case, because the initial height is given as 1 meter and our coordinate system has y equals 0 at the ground level, the initial position is 1, so the position at any time is 1 minus 4.905 t squared. If we assume that the coordinate system has the 0 value at the ground, what's the position going to be at 40 seconds? Mathematically, yes. But physically, where's that ball going to be after 40 seconds if you drop it from a height of 1 meter?
On the ground.
It's going to be on the ground. So one of the things you got to pay attention to is the problem. Because you can solve a problem and come up with a correct mathematical answer that makes no sense at all, right? You drop a ball from a height of 1 meter and wait 40 seconds, that ball is not going to be whatever that, 20 meters below the ground, right? It's going to hit the ground and stop. Now, if you're standing on the top or the edge of El Capitan in Yosemite National Park, and the ground there is 1 meter, you drop it from 1 meter there, maybe it will fall. It will be 40 meters below the ground you're standing on because you're dropping it off a cliff. But you have to, so you just have to pay attention to what the problem is so that your answer makes real sense, physical sense, not just mathematical sense. Does that make sense? Question?
Well, no question.
All right. So when does the ball hit? So we figured out the function for velocity. We figured out the function for position. And the next question is, at what time does the ball hit the ground? What time does it reach y equals 0? Well, this is the point. We're going to solve this equation for t, knowing that the initial elevation or initial position is 1 meter and the final position is 0 meters. So y of t is equal to 0. And we plug that in and solve this equation for t, and it's the square root of 1 over 4.905. It's plus 0.452 seconds. Mathematically, you could say minus 0.452 seconds, but that doesn't make any sense again. It doesn't make any physical sense, even if it's mathematically correct. So, and I will say that in my experience, one of the very common issues I find in engineering students is that they can solve the problem, and they come up with a number that makes mathematical sense, and they think they're done. But you've got to go back to make sure your answer makes physical sense. And this is true whether you're doing integrals by hand or you're using some software package, StadPro or SolidWorks or Swim or some other software. You've got to make sure that the answer makes physical sense. Okay? All right. So let's take this one step further. And again, I think this was a problem that was solved when you were talking about derivatives. If we throw the ball up in the air, we start with the ball at the ground. Y of t equals 0. We throw it up in the air with a velocity of 4.43 meters per second, and the acceleration in the downward direction is 9.81 meters per second squared, so it's minus 9.81 meters per second squared. Find a function for velocity and y at any given time. So we go through the same process. The acceleration is equal to the change in velocity with respect to time, which is minus 9.81. We integrate both sides, and we come up with the same formulation we came up with in the previous example. It's the function of velocity with respect to time evaluated from 0 to t is equal to this function, this integral of acceleration, which is minus 9.81 times t, evaluated from 0 to t. So when we evaluate that, the velocity at any time minus the initial velocity is equal to minus 9.81 t. The 0 drops out. In this case, the initial velocity is not 0. It's given as 4.43 meters per second. So we can plug this in to this equation, and we come up with our final answer that the velocity at any time is 4.43 minus 9.81 times time. All right. So if you solve this problem at various values of t, 0, 0.5, 1, 1.5, 2, 2.5, what you'll find is the velocity starts at 4.43, and what's going to happen to the velocity over the first second or two? You had a question over here?
Yeah. But you could have a negative velocity. I mean, unless t time can be a decimal, which it probably won't be. Maybe negative.
Yes, it will. But the negative velocity simply means that it's going down. So you think about when you throw a ball up in the air, what happens? You throw it up with some initial velocity, and it immediately starts to slow down, right? Until it reaches some peak where the velocity is 0, and then it starts to come back. As it's coming down towards the Earth, that velocity is negative. So again, as you plug in these times, and they could certainly be decimal. You could do this in tenths of a second or hundredths of a second or milliseconds, and develop a very nice curve of what velocity looks like. And it's going to go from 4.43 to 0 over some amount of time, looks like maybe half a second. And then it will increase again until it reaches some maximum or hits the ground. All right. There we go. So now this is our function of velocity. We can integrate that to get position at any time. So again, the integral of the position, the derivative of the position with respect to time is simply equal to the position. And this is the function we need to integrate with respect to time. What's the integral of this function? What's the integral of this function? Who can, somebody in the back. Here, in the red temple shirt.
4.43 t minus 9.81 divided by 2 t squared.
Yes, all right, so there you go. So these are pretty straightforward integrals. I just told you what the integral of dy dt is. So this is the integral of acceleration. This is the integral of the derivative of position, evaluated from 0 to t. Again, if you plug 0 into this function, it goes to 0, so we can drop that out. And the position at any time minus the initial position is simply equal to this function. In this case, what's the initial position? 0, because you're starting from the ground. Now, you could argue that if you're throwing it up, the position is, whatever that is, 4 feet, 3 feet off the ground. But in this case, the initial position is given as 0. So now we can find the position at any point, and you can plot that and get a nice curve. And if you plot it with, if you plot this at relatively small values of t, you can then use that curve to determine the position at any time graphically. You can do that graphically by reading a number off of a curve. But you're not going to be able to solve this. To do that, you have to have fairly small values of t. Yes?
The negative 4.905 t squared comes from the negative 9.81.
Yes. Yeah. Oh, here, this should be t squared. Yeah, I found it back here, though. All right. So we can go through this mathematically. We can use integration. But the integral is simply the area under the curve. And so the change in velocity is the area under the curve when you plot acceleration versus time. And we can use that to figure out the velocity at any given time. So if you plot acceleration, the area under that curve is the integral of acceleration, which is the change in velocity with respect to time. So if you have a simple function, you may not need to go through the integration. You might be able to use the plots, figure out the area under the curve, and that's going to give you your answer. But you need to understand the integration because lots of functions aren't simple enough to solve graphically. So again, a of t is equal to the derivative of v with respect to t. And the integral of a of t dt is equal to the integral of dv dt. This is a of t. This is the integral of a of t, that area under the curve. So that integral is simply equal to the change in velocity. We solved this mathematically, and with that in mind, we can figure out the area under that curve and solve the problem graphically. This is really just a repetition that change in velocity is equal to the area under the curve. And I'm kind of harping on this, I'm kind of emphasizing this because, as they said in the book, you don't need to use complicated integration all the time. You need to understand it because sometimes you will need to know it. But if you can solve a problem without integration, why not solve it that way? Now, certainly in this course, you're going to be told at times for your homework, for your exams, solve this mathematically, solve this using integration. And you can't go through the process of coming up with a bunch of rectangles or developing the area under the curve. But when you get into other classes, that's certainly appropriate. So in this case, this area is the area under is the change in velocity. If you plot velocity with respect to time, that change in velocity is the difference between v1 and v2. If you know what v1 is and you know what the change in velocity is, you can get v2. And that's really going back to algebra. Similarly, if we plot velocity with respect to time, the area under that curve is position, the change in position, because the area under the curve is the integral of velocity, and the integral of velocity is the change in position. All right, so this is basically what I just said. So let me move on and let's see. Use this in an example. And then this, again, is right out of your textbook. Notice that, so the problem here says you've got a car that accelerates from rest. Let's see. The vehicle starts from rest at some position x. It accelerates for 2 seconds. It then moves forward at a steady speed for 2 seconds and then decelerates for 2 seconds. It's a pretty simple curve. I mean, it's really easy to figure out the area under that curve, right? It's a rectangle. It's the width times the height. So we can use that area under the curve to figure out the velocity and the position at any given time. So the velocity is equal to the integral from a to t dt. For the first 2 seconds, now this is a problem where you have to solve it in parts. You can't solve this as a single equation. There's 3 separate parts to this curve. Each have different areas, and so you've got to solve this problem in three parts. In the first part, from 0 to 2 seconds, the velocity is the integral of at dt, which is the area under the curve from 0 to 2 seconds. What's the area under that curve? 4. So the velocity at time 2 is equal to 2 meters per second squared times 2 seconds. It's 4 meters per second. Now this is assuming that the velocity at time t equals 0 is 0, and we can assume that, well, we're not assuming it, we're told that the vehicle starts from rest. If this problem said that the vehicle starts from 65 miles an hour and accelerates for 2 seconds to pass a truck, then this velocity is going to have to be added to the initial velocity. So this is for the first 2 seconds. What happens over the next 2 seconds? What's the velocity at time t equals 4? It's not zero. The change in velocity is zero. This is an acceleration curve, right? So the change in velocity is zero. So it's 4 meters per second. From 2 to 4, from time 2 to 4, the acceleration is zero, and so the integral of a of t dt from 2 to 4 is zero, because you're taking the integral of 0 dt. Well, if you go through the process, the integral of 0 times t to the 0 is 0 times t to the 1, which is 0. So if the initial velocity at time 2 is equal to what am I missing here? I missed a step. The velocity at time 2 is equal to 4 meters per second. Then the velocity at time 4 is equal to 4 meters per second. Right? Yes, because we're going to add 4 to get, yeah. So, at time 4, we have a velocity of 4 meters per second, and then over the next 2 seconds, the car decelerates. So from time t equals 4 to 6, the acceleration is minus 2 meters per second squared. The integral from 4 to 6 of minus 2 times dt, the area under the curve, 2 meters per second squared, minus 2 meters per second squared, times 2 seconds is minus 4 meters per second. So the change in velocity from v equals at time 6 minus v at time 4 is equal to minus 4 meters per second. At time 4, the velocity was 4. So at time 6, the velocity is 0. So this is a pretty straightforward way when you've got a relatively simple function, a relatively simple curve. It's really easy to come up with the area under that curve, and you can use a graphical method to integrate the equation. So in this case, when we plot velocity, we start out at velocity equals 0. It increases linearly because the acceleration is constant. So it increases linearly for 2 seconds and reaches a velocity of 4 meters per second. For the next 2 seconds, the acceleration is 0, so the velocity is constant. And then for the last 2 seconds, the car decelerates at a constant rate of 2 meters per second. And so the velocity at time 6 is equal to 0. So again, this is a fairly straightforward curve. It's pretty easy to integrate that graphically, right? So we can integrate this curve to figure out the position at any time. The integral of acceleration gives you velocity. The integral of velocity gives you position. So how would you integrate that curve? Who has the sign-in sheet? Somebody, can you sign that down this way, please? How could you integrate that curve? Yes. Okay, how do you take the area of that? 1/2 the height times the sum of the bases. This is at 2 seconds. This is at 4 seconds. 2 plus 6 times 1/2 plus 4. Yeah, the area under the curve. So explain this to me, because I'm confused. You might be right, but I'm confused. The area of a trapezoid. Okay. All right. You could do that. So that would be, to me, the simple way. if you don't remember the formula for a trapezoid, which I don't remember, which is why I was confused. I know the formula for a triangle, and I know the formula for the area of a rectangle. Those are easy enough. So you can solve this in parts as well. If you know the formula off the top of your head for a trapezoid, that will work as well. So we take the area under this curve to figure out the position at any given time. So from 0 to 2 seconds, the velocity is linear. It increases linearly. So x is a quadratic. It's the integral of v of t dt. Because the area under this curve, under this trapezoid, gives us position. The area under the velocity curve is the integral of velocity. And the integral of velocity gives us position. So if we do this in parts, the first part gives us a triangle from 0 to 2 seconds, because the velocity has a linear a function here. And so we can integrate this as a triangle, 1/2 the base times the height. So the position changes is the integral of that triangle. The integral of that triangle is 4. So the change in position from x equals 0 to x equals 2 is 4 meters. And if the initial position is 0, then that car has moved 4 meters. The position at x2 is 4 meters. For the next 2 seconds, the velocity is constant at 4 meters per second. So the area under this curve is 4 meters per second. 4 meters per second times the time differential, which is 2 seconds, which becomes 8. And the change, or the difference in the position, is equal to 8 meters. The initial position, you started with x2 right here. You were starting at 4 meters. By the time you get to x4, you're 8 meters further down the road, so now the position is 12 meters. And that position is changing linearly. Did I not? I don't have a slide in here for the last. So the last section would be, again, the area under that triangle, 1/2 the base times the height, which is equal to 4 meters. And so from x4, from this position to this position, x6, the change in position is 4 meters. Add that to your initial position, and you end up with a final position of 16 meters. And when you plot it, that again is a quadratic. The car is slowing down, following this curve. This is linear in the middle, and you can plot the position graphically. So again, the integral of the area is the velocity, and the integral of the area is the integral of acceleration is velocity, and the area of the curve under the acceleration function is equal to the integral of acceleration. All right, so I think that's all I've got. Are there questions on this? Is it completely confusing, easy as pie, or somewhere in between? What was that? In between? Okay. Well, I guess that's good. If it was too easy, you wouldn't need to be here, and if it's too complicated, I'm not explaining it right. Questions? All right. On Wednesday, you've got your exam. As I said last time, the exam will cover up to derivatives. Somebody's trying to break in. They think it's a bank vault. It will not cover the integral information. That will be covered on the next exam. Up through derivatives. I'm not sure if that's chapter 8 or not, to tell you the truth.